So in this part of the video, let's carry out the calculation. So we have so far computed y squared x cubed and n squared x just via these simple formulas here. And we want to manipulate these formulas a little further. So the first thing that we did was, if we expand this numerator here, we get a squared plus 2ac plus c squared. And there's another thing that I want to use, namely, remember that we have this right triangle here, A, B, and C. Its area is n, so that means that n is equal to AB over 2, which is the same thing as saying that n over b is equal to a over 2. Okay, so we have such a relationship. So here I'm going to use this relationship for one copy of n over b. We have 4 copies of n over b, right? It's n to the 4th divided by b to the 4th. But I'm just going to separate n cubed over b cubed, and then I have one n over b left over, and I'll replace this n over b with a over 2 here. So using this relationship right there. Okay, if we do then a little simplification here, it just sees that the 4 and the 2 cancel, so you just get 2 here. And then we multiply everything out, and we get 2n cubed a cubed, 2n cubed a cubed, because that's the a times a squared. Then we get this 2 times that 2 gives us 4n cubed a squared c. The a squared comes from this a and this a, c. And finally this term times that gives you 2n cubed a c squared. So everything is divided by b cubed. Okay, let's now expand the x cubed. So this is what we have for x cubed. So remember, x was just n times a plus c over b. So if we expand that, we get n cubed, and so this is just a cube of a sum, so it's a cubed plus 3a squared c plus 3ac squared plus c cubed, everything divided by b cubed. And now if we just multiply the terms out, we get n cubed a cubed plus 3n cubed a squared c plus 3n cubed a c squared plus n cubed c cubed. Everything divided by b cubed. And finally, I want us to look at n squared x. So that's n squared times, and remember x was just n a plus c over b. So altogether we get n cubed a plus c over b. If you multiply this out, you get n cubed a plus n cubed c over b. And now I want to get a denominator the same as I have here. So this denominator is b cubed, here it's b. So I multiply top and bottom of this by b squared. So that gives me the desired denominator of b cubed. And I have a b squared appearing everywhere in the numerator. Okay? But remember that a, b, and c are sides of a right triangle. So that means b squared is equal to c squared minus a squared. So in fact, everywhere I see a b squared, I'm going to plug in c squared minus a squared. So if I do it here, if I replace this b squared by c squared minus a squared and multiply it out, I get n cubed a c squared minus n cubed a squared. Right? Now these two terms taken together, if you take out n cubed a from them, you just get c squared minus a squared, which is that b squared. And you do the same thing for this. So you replace b squared by c squared minus a squared, and if you multiply it out, you get n cubed c squared c, so n cubed c cubed, minus n cubed c a squared, everything divided by b cubed. Okay, what's the point of this? Well, I want to now subtract these two. You still don't know what the point of this is, right? I'm not telling you what the point of it is. You'll see in a second why I'm doing all this. So x cubed minus n squared x. I'm subtracting these two. Alright, so now I have, so this is this expression minus that expression, and I circled here the like terms. So first of all, we have n cubed a cubed. so that's here in this brown circle, minus, this is also n cubed a cubed, but with a minus sign. So when I subtract, I get 2 n cubed a cubed. So that's what you get here from these two brown ones. N cubed a cubed minus negative n cubed a cubed gives you 2 n cubed a cubed. Now this n cubed a squared c, I have 3 of those here, and I have an n cubed a squared c here, again with a minus sign in front. So when I subtract, I get 4 n cubed a squared c. So that's this here, that green circle. Then I have 3 n cubed a c squared, and I also have an n cubed a c squared here. Now this time with a plus sign, so when I'm subtracting, the 3 minus 1 becomes a 2. So it's 2 n cubed a c squared. And lastly, I have n cubed c cubed here and here, but because I'm subtracting, they just cancel out. So this is all that I get from x cubed minus n squared x. But that expression is already present somewhere on the board. If you look for it, you'll find it here. No, this is exactly the same as that. Every term is exactly the same. But what is that thing? That is y squared. So that means that this whole thing is equal to y squared. So if we make that substitution, right, that the substitution here is, the substitution was x was equal to n a plus c over b, and y was equal to 2 n squared a plus c over b squared. If we make this substitution, then we get that equation. Then y squared is equal to x cubed minus n squared x. But what is this? Well, by now you recognize this is an equation of an elliptic curve. So every such triangle, right triangle with rational sides a, b, and c, such that the area, so ab over 2, is equal to a positive integer, gives you a point on this elliptic curve. So let's write this down as a conclusion. And in fact, I'm going to write down a proposition here that will say a little more than what we just did here. So this calculation actually gives us one direction of this proposition. All right, so proposition. So let's formulate it this way. Let n be a positive integer. There is a one-to-one correspondence between the following two sets. Okay, so the first set is a set of triples. You can think about it as the set of these right triangles, A, B, C. These were the sides of this right triangle. A, B, C, these are rationals. So I'm just going to write it like this. A, B, and C are rational. They are positive rationals, in fact. And we have a squared plus b squared is equal to c squared, and 1/2 ab is equal to n. And then we have the set T, which are these points x, comma y, and they are also rational, and y squared is equal to x cubed minus n squared x, and y is positive. Okay, so what have we actually proved? And there's actually, so let me give you the formula, right? How to go from one set to the other. We already have one way here. So to go from the set S to the set T, so given A, B, and C, how do I get x and y? Well, this is the formula here. So x is equal to n A plus C over B, and y is equal to 2n squared A plus C over B squared. Right, you see that, so A, B, and C are all positive rationals. So what you get here, and n is a positive integer, so what you get here is a positive number and a positive number as well. Hence this, you definitely end inside this set. So there is a way back. If it's a one-to-one correspondence, then if I give you ABC, you should be able to compute x and y, so that's what we did here. But also if I give you x and y, you should be able to compute ABC. So there is a way back, and we're not going to derive this, but let me just tell you how to do this, what the formula is. So you get A equal to x squared minus n squared divided by y, B equal to 2nx divided by y, and C equal to x squared plus n squared divided by y. So just to summarize again, so we haven't shown this direction, right? We haven't shown that this is what you, that given any element here, which has a positive y coordinate, any point on this curve with positive y coordinate, that you can get, and if you apply this map, that you get an element of the set S, but you can check it. So we're not going to do this. So to summarize, what we have is, we're saying that you can think about these triples, A, B, and C. These are positive rational numbers, but you can also think about them as these right triangles with area n, and these are the sides, A, B, and C, rational sides. So there are as many such triangles as there are points, rational numbers, x and y, that satisfy this equation with positive y. So in particular, so let's write one corollary here. To this, which I'm going to state as a theorem actually, but it's just an easy corollary to what we have done. Theorem. Let n be a positive integer. Then n is a congruent number. If and only if the elliptic curve y squared equals x cubed minus n squared x has a rational point. With both positive coordinates. Actually, let me introduce here another restriction just to be sure. I don't think it's necessary, but so just take both x and y to be positive rationals. Okay, so we don't actually need that point. So positive rationals. Right, so why is that? So suppose that I have a congruent number n. What does it mean to have a congruent number? That means it is the area of some right triangle whose sides are rational, a, b, and c, and whose area is n. So if I have a congruent number, so if n is a congruent number, then there are a, b, and c that satisfy this and that. Right? That's the point. If n is a congruent number, there is a triangle that has rational sides and area equal to n. So if n is a congruent number, there are a, b, c positive rationals such that a squared plus b squared equals c squared and 1/2 ab is equal to n. So if there is such a triangle, then according to this recipe, we get a point on this curve whose both coordinates are rational, right? That's the point. That is the point. A, B, and C are rationals, so this is rational and that is rational, and these two x and y satisfy this equation. So that means that there is a point on this curve, y squared equals x cubed minus n squared x, that have both coordinates being rational. On the other hand, according to this map the other way, if I take that elliptic curve for some given number, and I don't know if it's a congruent number, right? For some n, so let's say n equal to 5 or something. So I'm looking at y squared equals x cubed minus 25x if n is 5. All right? So if I am able to find a rational point on this curve, so if I'm able to find x and y, both positive rationals, that satisfy that equation, then according to this recipe, I will get a, b, and c. And this a, b, and c satisfy that and satisfy that. So that means I will get a triangle that is a right triangle, has rational sides, a, b, and c, made up of these x's and y's, and the area is equal to n. So, in other words, n is a congruent number if and only if this elliptic curve has a rational point with both of the coordinates being positive. So, it's a very interesting relationship, okay, between a very old problem about a very simple one that you can explain, as I said, to a kid, about finding which numbers, which positive integers actually are areas of right triangles with rational sides. And you have now this problem translated into a problem about rational points on elliptic curves. Why is that a valuable thing? Well, first of all, I would claim that the most valuable theorems in mathematics actually all are about linking two things that do not look on the face of them as if they had something to do with each other. Okay? So here we're linking some deep problem about congruent numbers to another deep problem that concerns elliptic curves. We didn't see that bridge before, now we see there actually is a bridge. So that is, I think, valuable on its own, and we could have discussions about it. I would argue that this is probably what most of the theorems in mathematics, most of the important theorems in mathematics actually prove. Some connection between two notions that are defined in different ways. However, there's also a practical side to it, namely, if we want to now actually answer some question about these congruent numbers, we can use the tools that people developed for elliptic curves. And maybe some of these tools will actually be useful in answering some questions related to these congruent numbers. So in the next part of this video, I'll show you one such problem regarding the congruent number 6 that can be answered using this translation.